Hello, my name is Brian Doe, and I'll be presenting my work on dynamically reconfigurable discrete distributed stiffness for inflated beam robots. I'll first begin by providing an overview of inflated beam robots and discussing current limitations. I'll then move on to explain how our method for scalable stiffness control works, and finally show results from a series of demonstrations we conducted. So, to begin, what is an inflated beam robot? As opposed to most manipulators or robots, which feature rigid supporting structures, inflated beam robots are characterized by their use of internal gas pressure as the main supporting element. Because of this, inflated beam robots can provide inherently safe human-robot interaction due to their compliance and low inertia. Their low weight allows them to be made extremely thin and long, giving them high aspect ratios well suited for tasks such as inspection, as can be seen with the AIA robot on the left and the lighter-than-air Giacometti arm on the right. One subclass of inflated beam robots are those which can invert material at their tip via pressure-driven eversion. In addition to possessing all the properties I discussed previously, they can lengthen by pulling material through themselves at their tip. Due to their similarities with vines, we refer to this class of robots as vine robots. Now, inflated beam robots do possess some key limitations. The first is that they can buckle under a sufficient outside force. The second is that there's a trade-off between the simplicity of these robots and their dexterity. To achieve a highly dexterous robot with many degrees of freedom, or DOFs, past robots have required the use of either actuators at each joint in the arm or cables which run from each joint to motors in a stationary base that transfer forces to the cables. However, these approaches can add significant weight and complexity to these otherwise inexpensive, simple robots, since having n-controllable DOFs now requires n actuators, with all the supporting equipment that entails. One approach to simplifying the design of robots with a high number of controllable DOFs is using activators in addition to actuators. Activators are simple devices which do no work on the environment, but modulate the output of actuators. Thus, by using many simple activators, we reduce the number of complex actuators needed. Jamming is one approach which has previously been used to modify actuator output in robots. Jamming is a technique seen within soft robots which involves generating a normal force on layers or particles. This compresses them together, increasing the friction force between them and thus the overall structure stiffness. One example of this approach is in this robot with jamming cells, which was used to allow for amoeba-like motion with only one actuator by stiffening certain cells while leaving others compliant. However, jamming has traditionally been limited by its requirement for a low-pressure source, often in a vacuum, as well as the valves and vacuum lines in order to generate the required pressure gradient, as can be seen with the red vacuum lines tethering the robot on the right. We further build upon this actuator-activator paradigm to produce a tip-everting inflated beam robot with a highly scalable method for discrete distributed stiffness. Here's a picture of the overall system. At the base of the robot are two spooled motors which are used to actuate the robot into a variety of shapes. With our distributed stiffness method, these two actuators can control a high number of DOFs, as I'll show later on. I'll now explain the method we use to achieve stiffness control. Here is a schematic of a cross-section of our robot. We first begin with an inflated tube. We configure the tube to allow for pressure-driven tip eversion, which results in inner material that is pulled through the length of the robot. To this, we create a series of airtight chevron-shaped pouches which we embed into the tube's walls. Inside each of these pouches are 4 sets of parallelogram-shaped fabric layers arranged circumferentially around the robot. These layers can be jammed or unjammed using passive bistate valves. Each pouch contains 2 valves, one to allow airflow from the high-pressure robot body into the pouch, and a second to allow airflow from the pouch to the lower-pressure atmosphere. Finally, we have an electromechanical carriage which we use to activate the valves. The carriage has motorized rollers which allow it to ride along the inner vine robot material, which has not yet been inverted. The carriage also carries an electromagnet, which is used to switch the state of the valves. In this way, we do not need to wire each valve, greatly simplifying the design. As the carriage drives along the length of the robot, it can selectively stiffen or unstiffen certain pouches. Here's a video of the carriage driving through a clear robot body. The carriage itself is 3D printed, and it's powered by a set of wires connected to the base of the robot. As I said before, the pouches can stiffen, and we can do this through layer jamming. However, we don't need to use a vacuum source. The nice thing about jamming is that it just requires a pressure gradient, and since we're dealing with an inflated beam robot, we know that the inner robot body is inherently at a higher pressure than the atmosphere. Thus, we can use the atmosphere as our low-pressure source. Here's a schematic which demonstrates how this works. By activating the desired valve, we can switch the pressure in the pouch from the higher pressure of the inflated beam robot to the lower pressure of the atmosphere, which causes the layers to be compressed together, stiffening the pouch. Each of these valves is extremely simple. They're passive bi-state 3D printed valves, and each contains 2 sets of O-rings and a magnetic ball. In the presence of a pressure gradient, the difference in pressure results in the ball being pushed against the O-ring, creating a passive seal and preventing airflow. However, we can switch the valve state using an electromagnet. By bringing the electromagnet towards the valve, we can attract that magnetic ball, pulling it away from the O-ring and allowing airflow through the valve. Now, if we were to remove the electromagnet, there's no longer a pressure gradient to push the ball against the O-ring, and thus the valve would remain open. Through the use of these simple, inexpensive valves, we can achieve jamming without the need for any wires or pressure lines. The only wires needed now are those for the carriage, and as a result, we're able to easily scale this method to robots of multiple meters in length. We conducted 3 sets of demonstrations and experiments with our robot. The first was active shape change and reconfiguration. Now, in the introduction to this talk, I previously stated that buckling was a limitation of inflated beam robots. However, now we leverage buckling to produce virtual joints along the robot length. To do this, we stiffen all sections along the robot except for the section where we want the virtual joint to occur. We then apply cable tension via motors at the base. This then causes the unstiffened section to buckle, and we can control the angle of buckling by controlling the amount of cable tension we apply. After a buckle is formed, we can re-stiffen that section, locking the bend in place, and repeat this process sequentially along the length of the robot, allowing us to configure the robot into a desired shape. To produce a new shape, we can unstiffen all sections and reintroduce slack in the cables to allow us to repeat this process. This allows us to produce a number of different shapes using the same robot and only 2 actuators. The second experiment we conducted was investigating the ability of the robot to resist a cantilevered load. By jamming all pouches along the robot length, we can increase the global robot stiffness, reducing the deflection as compared to an unstiffened robot. We can see the results of this experiment here. Even at relatively low pressures, we see that there's a major difference between the jammed and unjammed robots, and whereas the unjammed robot buckles at lower pressures, we can avoid this with the jammed robot. Finally, we demonstrate that this distributed stiffness method is compatible with pressure-driven tip inversion. The video on the left shows how the 4 sets of layers still allow for growth at the tip. We can imagine that as we grow, we can use the virtual joints to allow for navigation while stiffening the robot to traverse larger gaps without buckling. This concludes the presentation. Thank you for watching, and I'd like to thank my co-authors as well as the NSF and TRI for their support. Thank you.